Welcome to Across the Opti-Verse, where we're bringing our team of in-house specialists to you.
We're going to talk AI, model operations, and simulation engineering.
Today's episode, Dean will be interviewing our in-house specialist on simulation engineering.
Correct.
Lethabo.
We hope you enjoy it, guys. It's a great episode, and let's get right into it.
Find us wherever you listen to your podcasts. Cheers.
Welcome, everyone, to the next episode of Across the Opti-Verse. This is a really, really great episode. To give you context as to who's sitting next to me, and I will introduce him shortly. Last year, I was challenged by our CEO and director, Grant Robelaar, to build a full VTOL, which is a vertical takeoff and landing UAV through simulation engineering. And it freaked me out. I'm a mechanical engineer. I know nothing about planes other than they go up and they go down and they get me to places safely. And I then started building with this example. And whenever I got stuck, the person I came to talk to was Lethabo. Lethabo is our resident simulation engineering expert, among a few other ones at Optinum, but knows so much about it, knows so much about model-based design, about how to set up complex physical models in aerospace and actually make them somewhere where you can be innovative, where you can design, where you can do crazy cool things without having to do that expensive traditional way of building, finding out what doesn't work, having to go back to the drawing board. So now to introduce who's sitting next to me, this is Lethabo. He is an aeronautical engineer. He graduated from the University of Witwatersrand in Johannesburg in 2022, but he actually was with Optinum a little bit before. He was one of our VACwork students in 2018, and he actually built a robotic arm with one of our former colleagues, Praneeth Kala, who is now in Sweden, actually. But what's really exciting is that Lethabo knew the company, came back, and now we get to use him and get his advice and his expertise, which is what I just always lean to whenever I'm stuck in simulation engineering. In various projects, I know you've worked with research institutions, you've worked with aerospace and defense clients, government, commercial. It's just so amazing, the breadth of knowledge you've able to get in the short time you've been with us. So I know I've already tooted you up, get you very excited to listen to more of him speaking. I'm going to stop talking. Lethabo, maybe you can tell us a bit about yourself.
Cool. Yeah, thanks for having me. As you said, I am here today to talk about model-based design, simulation engineering, but also most important to share some experience of some of the things that I've done, especially in the aerospace and defense side of things.
Yeah.
Something about me that's quite cool is that here now I am a senior consultant at Optimum Solutions, and I focus primarily as a as a model-based design specialist here. And I just help our aerospace and defense clients, with all their modeling, whether it be optimization, trying to figure out what their POCs will look like, proof of concepts, or what their products need to look like, what is it they want to achieve, what they're trying to do. But most importantly as well is just trying to bridge that gap between the knowledge required for the design process and the tools that we use as well to actually implement those ideas that they have. And so from the few years that I've been here, some of the things that we get to see, especially in the more the commercial side, which is probably the most interesting side, we get to see some people develop very cool and interesting things, get to meet them as well. So being a part of different kind of concepts, let me say, has been quite fulfilling, and kind of experiencing that, what is it that you can do better, but most importantly, from a time and monetary kind of idea, what are the constraints that we're facing, and how can we meet our deadlines as soon as possible? And that's where we come in to kind of leverage our understanding and their expertise. And so I fall in mostly. Yeah, so it's been quite a fulfilling kind of role.
I'm sure it's been a busy role as well. A lot of people come to you when it comes to anything to do with simulation engineering.
Yeah.
Okay, so today I thought we had a idea, basically what I went through last year, but what a lot of people are talking about, this is a very popular topic of UAVs and how we can use them in commercial spaces to help improve various kind of industries. What we want to talk to today is get your advice on the steps we need to take, best practices, wherever they can be, and advice you can give on creating a UAV step by step. I think the important part is, and this is something we've discussed before this session, is when someone says UAV and drone, I think to the average person, same word.
Yeah.
But what is the actual difference between a UAV and a drone?
Cool. So they are used interchangeably in most domains, but from a commercial perspective, oftentimes we use UAVs to mean unmanned aerial vehicles, but they can also be autonomous. They don't need to be on a ground station. They could be literally flying on their own, but also they can vary in size. Whereas drones are more, for your hobbyists and small retrofitting things on it for farming, for instance, maybe. Those we'll consider more your hobbyist drones, as the word would suggest. And primarily, it's all about size and how long it can actually stay up in the air. So most drones will not stay up in the air for like an hour, probably less than that. Whereas your UAVs, which depending on what they're made for, whether it be for combat, for military, for reconnaissance, whatever platform it is that they're trying to use it for, they could be there for hours, days, months, and they are quite large. And they also form part of things that have different kind of purpose as well, but also the structure is different. So you have, your helicopters, you would say they can also become UAVs, you can retrofit them as such, but you also have your fixed wings and variable wings as well, which can also be UAVs depending on the purpose again. So it's mostly about size, but also industry prefers the word UAV.
Okay. Oh, awesome. Okay. That's very cool. Kind of sets the scene of when we say UAV, we're talking larger scale, more commercially usable for industry rather than for, let's say, someone who wants a drone to track them on their run or to follow them on a hike. Okay, very interesting. Okay, cool. So let's say when you get approached by a client, approached by anyone, or yourself, you're thinking about it, you want to build a UAV. What are kind of the first steps you take from, you've just got this idea to now getting it to start the process?
Right. The first thing that I always ask is, what is the purpose? Because purpose will define what the end goal needs to look like, what the end goals need to look like, and what the design process ends up looking like as well. So when we look at, for instance, you want to build a drone for farming, for instance, in this context, you would have to think, okay, what are the weight requirements of the stuff you need to add, or the equipment that needs to be attached to it, for instance. If you're looking at a UAV, maybe it's for reconnaissance. What is the equipment you need to add onto it, like the cameras and so on? And how long does it need to be up in the air? So it's all about purpose and what environment needs to operate in that you need to first kind of understand and ask about. And then from there, you're able to determine, okay, if this is the purpose of it, then this is the standards or the body that you need to look at. Which authority are you actually going to kind of talk to understand what the requirements need to be? What are the standards I need to use? And what are the kind of concepts I need to be thinking about? And who can I go to get more information and examples? We feed from examples often.
Yeah. Okay, cool. It's really interesting. So essentially that first step is research into the environmental requirements that you could potentially set yourself based on where you wanted to operate, but also some sort of regulatory body that sets requirements for commercial use of the UAV in the industry and the specifics. That's really, really interesting. And it kind of sets up then your architecture of your solution. So when you're talking about these requirements, how detailed do you need to get them to be? Is it just like it must weigh less than 50 kilograms, or do you get even more detailed into components and subcomponents?
So ideally, you would look at the market first and say, okay, this is what's currently available in the market. What will make mine stand out? What is some of the cool features that I want to add onto my UAV that will make it a little bit more interesting for our clients, or interesting for your users, rather, let me say. So what we have to look at that first, and then after that, look at the regulatory body standardizes the sizes, standardizes the powertrain, standardizes all of these power plants and so on, to say this is based on this size is what you can use. These are the emission requirements. And we want to use it for catching or doing scanning, for instance. This is the kind of cameras we would use in our environments. So the regulatory body will actually tell you what most of the requirements would be from a very technical level, and will also give you what you need to test as well. From there, you can say, okay, if this is what I need to test, this is the requirement that actually needs to be there at that moment.
Wow. Okay. Amazing. That helps a lot in just understanding that starting position. Now, something that comes up a lot when, particularly commercial UAVs, I've had experience in aerospace and defense side of things, but there's talk of requirements and there's talk of testing and then there's talk of verification and certification. To me, at the start, they all seem like the same thing, but they're all very different and have different kind of scopes.
Yes.
What is the difference, if you can summarize that for us?
Right. So for the requirements, these are the standards and the processes and the numbers that you need to have to say this is what my product needs to do, needs to look like, needs to actually achieve as well. So all the goals, all of the processes, everything that required that's basically related to your product, that will be stated in your requirements step by step. But also above that as well sits what are the frameworks I need to use as well. So the framework will determine as well what the requirements will be. So for instance, communication protocols and all the other things like what the ground stations will need to look like for you to communicate with that. And what are the protocols around the bandwidth you need to use. So all of that will be part of the requirements. And once you have those requirements, you would look at what customers are using to build an architecture. An architecture will tell you who you need to work with, who are the suppliers, where can you get it from, what are the sizes of everything that you need, and how can they all communicate together. So an architecture is basically the plan of how your product will end up looking like more than anything. Then after that, you will look at traceability and verification. So with traceability, you're basically looking at your artifacts, all of the little documents that you have, all of the supply information, the specifications, all that stuff needs to be tracked so that when you go into the certification side of things, the authority will be able to tell you, yes, it meets these specifications, it meets these requirements. And based on our tests that we've done on our site, it does meet, it does pass all our ISO standards, for instance, in our case, which we use quite a few of them. And it's very important to know that all of these happen iteratively, but also it happens all the time, and they're all interlinked in some way or another, especially from a certification requirements and architecture perspective. You know, when you do verification, validation, and testing, all of that oftentimes I think will sit right at the end, but it needs to happen in every single stage. So that you're able to kind of get the most of the simulation engineering process as well.
So it seems like particularly that testing and the validation and verification is quite an arduous process. You've got to make sure it's very detailed, very rich with information, and correct.
Yes.
And so you want to do it at every step, otherwise it makes all that work come to the kind of end loaded, and then you're just stuck in creating artifacts and documentation.
Absolutely.
It does make me feel good that any UAV or any commercial drone let's not use drone, any commercial UAV or plane is really strictly regulated and tested to an absolute fine granular detail to ensure that it will do what it's supposed to do and it's safe. That's really, really good to know. I mean, I knew it, I always had the sense. It's now good to know that there's a bit more to it than just me thinking it. That's amazing. Okay. Important part is there are obviously critical things. There's design critical things that have to happen, and then there's some things, as you say, that differentiate you from the market, but might not be critical to the success of the product. How do you differentiate? And then also, how do you ensure you don't miss out on the critical things?
So the critical things are often based on what the standards are required to be. So oftentimes things like your speed, your altitude, the products you need to use, the communication platform, the range and all of that is often specified. And those are the most mission critical, is what I would say, because they determine the success of your product. Because if it doesn't get off the ground, it's not really
not a good UAV.
It's not an aerial vehicle. It doesn't get off the ground, and if it doesn't land, then we don't consider it as a successful product, because then you have to keep on rebuilding it. So that doesn't really help. So ideally, what we need to do is actually think about what are the critical things that I need to make sure that my product does the minimum as a minimum viable product. What does it need to achieve to become a minimum viable product? Before adding all those additional features that can help you stand out, it's important to have a viable product first. And then from there, then you can start differentiating yourself from the market. And it's always a good idea to look at prototyping as a very good way to get started. As often, you have your competitors kind of always working around optimizing, making things better, and every day thinking about maybe I could do this, change this specific aspect of my of my product to make it a little bit better. And using that information, going to expos and going to, events allows you to understand what the market is actually all about, understand what the diverse ideas that they have as well. Kind of builds an understanding of what it is that you're actually trying to do. And what's more important than actually being a differentiator is also what's also more important is actually figuring out what makes you really good at building a UAV, because that's probably the hardest part.
Yes.
Oh,
that's interesting. I mean, it's like the whole part of simulation engineering is to allow you to innovate.
Yes.
But you still have to do the groundwork. Get as you say, that minimum viable product really solid and good. And then the innovation comes naturally thereafter. And if you miss a critical step, maybe just a quick question, you miss a critical step. With simulation engineering, as I understand it, it's quite easy to jump back and quickly add it in without having to redesign a wheel. It's a quick, simple system, kind of add in a few calculation changes and it all works. Is that correct?
That is true. There is somewhat of a caveat towards that.
Sure.
Sometimes we think that retrofitting is a good idea. And unfortunately for some of these, especially for aerial vehicles or commercial kind of products, it's very hard to retrofit. So ideally you would try to have as many things kind of laid out for you to have already, kind of work on that and optimize. And then maybe if you've missed like a small thing, then you can of course think about coming back and trying to test it. But what's really nice about just general simulation engineering is that because it's not yet in a prototype phase in the physical world kind of thing, it's all computer based, you easily can actually go back and start iterating, start adding new things, and kind of, if you miss something, kind of go back before you end up having to spend all the money and actually doing prototyping, which becomes quite expensive if you miss something quite critical, because oftentimes, based on the standards, there are certain things you can't add later on. You have to add them beforehand, or else you have to redesign your entire architecture. It becomes very important to spend a lot of time in the initial phases of the requirements, the research, the literature reviews, understanding what the market is like. It's very important to spend a lot of time on that. And then after that, think about, okay, this is what I'm thinking about, this design philosophy I'm going to follow.
Yes.
And then you start doing your iterative design and adding the necessary teams and building up the virtual product and testing it as well. Then from there, you start thinking, okay, what did I miss? What did I do? And then once you're happy with everything, then you can move on. And say, okay, I'm ready for this to go into the world.
Yeah, that's really great. I think it's a good lesson for all the students that the literature review and the research actually does mean something. Don't get too excited and go straight to design. But that's really, really cool. So maybe when you get into that design and the simulation phase, I don't know what are the steps you need to follow, but maybe at the same time, I can ask you, what principles should you really adhere to when you're doing design and simulation?
Right. The first thing that I often get into is, what do you want the performance metrics to look like? What do you want out of the simulation? When it comes to building things like digital twins, it becomes very important to understand what is the end goal of that digital twin. Is it a mathematical model? Is it a physical representation of the end product that you do from some software that you're going to use? Is it a statistical model? It depends on what it is that you want to do. But in our case, for UAVs, you'll probably do some sort of physical representation of it and build your control systems, build your plant, and so on. Build all those to be as accurate as possible. So that when you're actually going to the deployment side, it is an accurate representation of what's already there, and that the testing is quite accurate as well. So it becomes quite important to do that. I think something that is always kind of overlooked as well is understanding what your environment is actually going to give you more than anything. So actually having, if you're going to fly over a very warm environment, you know that the air is not as dense. You need to consider, okay, it will actually affect my performance in this way from a UAV perspective. So it's quite important to know what is the purpose of your design.
Yes.
And anything.
It's always something I've traditionally had bad luck. I always forget about what happens outside of the design, because it affects the pressure, humidity, wind, all those things. That's really, really important. Okay. So maybe what's a common challenge in this? I mean, the textbook examples work perfectly all the time. But in the real world, particularly when you want to innovate, there's challenges. What are the common challenges that people face?
The most common challenge is understanding what the framework is all about. When we talk about the model-based design framework from a simulation engineering perspective, the most important thing is understanding that you need to be able to grow. You need to be able to iterate. You need to be able to have this agile approach to your workflow. So having hard-coded things, having underlying kind of S functions in our case would be, without actually understanding why they're there, copy pasting and all those things doesn't actually allow for the longevity of your project, because later on you want to kind of optimize, you want to change, you want to add additional features. That becomes very difficult to do when you have all these hard-coded things happening internally. So it's very important to have a way to make everything dynamic is the word I would use. So be able to change things as they need to be changed. That requires a little bit of understanding what that actually means for you, but also what it means for your team, what it means for the company as well. It's very important to understand what all those things are. And the second biggest challenge is the deployment side of things. Hardware is not the easiest thing to work with. We have different languages, and I've worked with C, C++, some HDL as well. All the communication standards as well. So it becomes very complicated to say, how do you decide what hardware am I going to use for this? You can just pull something off the shelf, but sometimes you need something very bespoke. And that means you need a new team to kind of come develop this hardware for you, kind of figure out, okay, this is my hardware team. They're going to be able to pull all this information in and build this beautiful system for me that will be able to answer all my problems. That becomes very difficult and arduous process, to be honest.
Okay. I mean, that makes sense. And I think, again, it goes back to this constant theme you bring up. Do the research at the start. It might seem tiring. It might seem a bit boring because you want to do the cool design stuff. Really spend all your time focusing on the entire pipeline. As you say, the model-based design framework, simulation engineering, essentially. Once you know each step and what's needed, you don't have to have every problem solved, but you really need a core understanding of your environment, your process, and your output. And how you're going to get it basically into a physical model. And then it makes the rest of the process easy. I think there's a key word you used there that I like. Design for longevity. Don't design for once off. I'm assuming there's a I know in the traditional kind of design sense, it was designed once off, and then when the next product version 2 has to come out, start from scratch. When theoretically with simulation engineering, you can already start 60-70% of the way, and now you start having fun. That's the way. I mean, that is amazing. Okay, cool. So we spoke a lot about verification requirements. I want to jump into the certification part of things. Why do we need certification? That's maybe the simple way to ask it.
So certification is quite a laborious process to get through. When we use the ISO 262, 2626, and we use ISO DL 178 and all these other standards, it's an arduous process because it's all about artifacts. What are your results saying? What is the performance metrics? What are your inputs? What are your outputs that you're giving it? Is it dynamic enough to handle any type of environment, or a subset of all of the requirements that you have? So when you go out into the real world, it's not an ideal environment. And so what certification is meant to do is help you figure out, what is the real environment actually going to give you? So things like, you have a gust of wind, what is that going to look like? You have terrible weather, what is that going to do to your UAV? So all of these are just design elements where it's meant to enforce a rigorous safety standards, rigorous performance standards, and very, very well understood dynamics of what we will provide you. That way, that, okay, if anything happens, you have fail safes. You have conditions to allow you to ensure that this can land safely. You have conditions that allow you won't lose anything or anyone, depending on the platform that you're working on. So it's very important that we always do these certifications so we can actually pass, but it also allows us to be more marketable. It's very important. Certification, if you are certified in any of these standards that are provided, you're able to go out into the world and say, hey, you can use my system because it's certified in this platform, and this allows you to be more global.
And maybe just to clarify, the standards, are they internationally recognized standards, internationally applied, or is it various? Does it change slightly between the bodies?
So different bodies have different standards.
Okay.
But for instance, we have the FAA, who use standardized using ISO, and the I in ISO stands for international.
Oh,
So
cool.
it's an international standardization organization, that's what we'll call it, although
Yeah.
it's in French, so it doesn't really sound like that. But it is all globally recognized,
Yeah.
and literally everybody appreciates having an ISO standards, no matter what it is, because
Yes.
it allows us to communicate with international clients. America uses metric system, and we're able to say, okay, this is the ISO standard that we're using. They're definitely also using the same one.
Yes.
So it allows us to work more internationally, to understand what globalization is all about.
Yeah.
So it helps quite a lot.
That's exactly it. It's it's important. I think to also clarify, some of these things we're going to build and things that are being built carry people, carry cargo, and some are meant for reconnaissance or carry cameras, but they all have rigorous standards from which they need to adhere to. And again, I think it's important, as you say, marketable. Everyone's building something to be commercially viable, and to be certified is a really major step. When you mention those artifacts, we're talking, it's as I understand it, it's documentation, correct? We're not talking like 2 or 3 documents. We're talking tens of thousands of documents. Really, really granular detailed testing. Yeah. I mean, that's the way to go.
Yeah, absolutely.
There's someone that has to read it, which is, I feel bad for them, but I get why they need this important job.
It's very critical.
Okay, yeah. Cool. Then maybe, in the interest of time, just checking how long we have left, I've got 2 questions. And we spoke about deployment, and we've spoken about the challenges of deployment, and hardware is, let's say, temperamental in its best of days. How can you test, essentially, without having to build a prototype, your UAV in mimic real-world conditions? What's kind of the approach there?
The ideal approach is to test each individual system. Okay. So in this case, you would have whatever your powertrain or your power plant is. In an aerospace kind of industry, is the power plant. So whatever your power plant is, you would test that separately.
Okay.
So that means if it's, for instance, motors, you would bring those motors in, connect it to the relevant hardware. And you haven't yet built it, but you want to test if it's actually going to work. Yeah. Connect it to the relevant hardware, and then you can generate code using your software that you built your simulation environment from. Generate the code from there, whether it be HDL, whether it be C, C++, any of those languages. Then you can send it through and see what the performance are like, especially from a control perspective. I think each and every system has a specific requirements. Communication will require bandwidth, range. Those are questions you're answering from a communication perspective. But when you have all the systems together, now it talks about interference. How do they all work together? What is the response times? How long does it take for me to get an answer back from my system?
Yes.
Based on all the other active systems that we have. There's a lot of moving parts when you're building a UAV. It's not just the motors or the propellers or the engines. It's also the communication that you need to do if you are 4,000, 400,000, 40,000, however many kilometers you are away from here.
Yeah.
How long does it take for you to communicate back, and what the regulations say about that as well? There's a lot of moving parts when you're trying to build the systems. When it comes to hardware, it's important to know that they all need to work together. So to test it, you would obviously try to build an environment that allows you to test all of them as often as possible. Yes. As you're slowly developing. So you ideally start with a control system. You see, okay, if I build this control system, is it going to work on this hardware? First question, you say yes, okay, cool. Then I can actually go and test it on there. Yeah. And bring out all that information that I need. And then afterwards, just build a small prototype. Usually you do scaling. So you won't build the full scale one, you build a small scale version of it as a prototype to say, yes, the performance is pretty good, and you can hopefully extrapolate and kind of scale it up to the relevant size so that you can have it for commercial use. Yeah. That's pretty much how hardware works.
Yeah. It's and I think important to clarify is that it's with simulation engineering, multiple teams working together, not just one person having to do it all. Yeah. That communication, that integration between the teams and between the parts is really important. Yeah. I think it's also is where you would do your software in the loop and your hardware in the loop testing, correct? Yes. Okay, cool. Okay, so to close off, maybe actually 2 more questions. Okay. I've lied when I said I had 1 more question. The second last question is, when you're doing deployment and going to hardware, how do you measure the success of that?
Okay, so success is measured on what the requirements you're specified actually say, which
Yeah.
is why it's again very important to go back and make sure that they're really good.
Yeah.
So the performance based on like the response times is such an important time. How long does it take for, if I say, okay, I want to take off, how long does that actually take? You know, that will determine the runway length that you're going to take off from, if it's a fixed wing, or how much space do you need, how much wind does it generate. So all of that kind of starts to play a role on the environment.
Yeah.
And becomes a lot more environmental as well.
Yes.
Apart from the fact that, yes, you have your performance metrics for the actual UAV, but the environment plays a much more significant role. So when you're trying to measure your performance and the success of your hardware integration, it comes into the ideas of, okay, is my code good enough? Is the response time, is the rate that my information is being transmitted efficient and up to standard? That's often the biggest hurdle, is getting that time, that response time, that iterative time, kind of to the right point where the information is not getting lost during transmission.
Yeah.
And not skipping any vital information from there. You know, especially as we move on to more, well, let's say space kind of frontier now, with some of our clients, we get to see that it's not just about having a good system, it's having a robust system more than anything.
I love that.
And it's very key that you, as you're building these systems, that you have that rigorous testing inbuilt, but sometimes it was important to have the good hardware as well to help you achieve the rigorousness of where it's going to perform. Because in space, you know, there's nothing there. It's all cold. So it needs to pass those tests.
Needs to pass those tests. Cool. And now to close off, we've got to just talk about the last thing. You've got so many years of experience in your brain, and you've got so much information in your brain, something you're passionate about. What's the one piece of advice you want to give someone who wants to start working in simulation engineering?
Don't be afraid to try. I think the biggest hurdle is you look at these already pre-built, you know, whether it be drones or UAVs, you end up being like, oh my goodness, this looks like a lot of work.
Yeah.
But the reality is that tons of examples. There are a lot of companies doing it. It's a good idea to leverage existing information, existing knowledge, to be able to build what it is that you're trying to do. And of course, not being fearful of that, there is some few things that you need to be, you know, a little bit more reserved about, but also more critical on.
Yes.
Is having a good body to be able to interrogate what it is you're building.
Yes.
You know, it means nothing to build something incredible, whereas you don't actually know it's going to perform well from an expert's perspective.
Yeah.
So it's very key to have that both sides of the coin kind of playing around, be innovative, but also be critical of what's out there and understand what's actually going to happen in the real world.
Yeah. No, thank you. I think that's a good point. And it's scary to try, but it does have its benefits.
Yes.
As someone who's done a little portion of trying, I really enjoyed it outside of the few days where I messaged you in fear. Cool. Well, Lethabo, thank you so much for your time.
Thank you.
Really appreciate it. I think anyone who wants to reach out to Lethabo loves talking about this stuff. I talk to him about it all the time, and I'm not the only one here. Please do. We would be so grateful for you to reach out and talk to us more about this. We want to talk more about this. I'm going to stop talking. Please catch us wherever you get your podcasts, and thank you so much for joining this episode of Across the Opti-Verse. We're about to take flight now. You now know how to make a UAV, so we're ready to go. But thanks, guys. Enjoy your day. Cool.